So now we're going to continue our look at hollow and complex shapes with a shape that's actually not necessarily hollow. It is a torus. So what is a torus? That's the mathematical term for a donut. So if you have a donut where you've got a large radius of b, and you have an inner radius of a, and you want to determine the volume of it, let's assume for some reason you can't just, drop it into a graduated cylinder filled with water and see how much the water level rises. We need to work it out from theory. So how are we going to do that? Well, we could do it similarly to the way we did the past example, where we've got a circle within a circle. This is the cross-sectional area if we cut it as most people cut bagels, where we go right through the center. So the line we've cut will come along the edge like this and along through the middle. So then the outer circle, if we're looking at it at the absolute peak, right in the plane, we're going to have the maximum width at b plus a and b minus a as our two radii. And then we'd be integrating that cross section this way. Now, when we're doing the volumes, as per usual, we are just going to do the volume of 1/2. So we're going to start at the 0 line. Our x-axis is going to come in this direction. And we always know at all points this radius is a. As we are integrating with respect to x, this would be x. So then this distance that we have going forward and back, that would be the square root of a squared minus x squared. So now this means that our volume is going to be 2 times the integral from 0 to x of the areas of this inner circle. And that area is going to be the area of the outer circle, b plus root a squared minus x squared all squared, minus the area of the inner circle, b minus the square root of a squared minus x squared all squared dx. Just to be clear, we'll put that entire integrand in brackets. So if we pull out our common factor of 2 pi, we have the integral from 0 and, sorry, we don't want to end it at x, we want to end it at a. Integral from 0 to a of b plus root a squared minus x squared squared minus b minus the square root of a squared minus x squared squared. All integrated with respect to x. So our next step is to simplify that integrand. So we're going to start off with a b squared. Then we're going to have plus 2b times the square root of a squared minus x squared plus the square root of a squared minus x squared squared, which is just a squared minus x squared. And now expanding the second, we're going to have minus b squared, and it's going to be almost the same. We are just changing the sign of that middle term. And that's integrated with respect to x. Now taking a look, we are subtracting the latter from the former. These b squareds are going to cancel. These a squared minus x terms are going to cancel. So subtracting 2b means that we're adding 2. We already have 2. So we have volume equals 2 pi times the integral from 0 to a of 4b times the square root of a squared minus x squared dx. Or, combining our like terms, 8b pi times the integral from 0 to a of the square root of a squared minus x squared dx. Now, with an appropriate substitution of variables here, for example, we could let u equal the arc sine of x over a. That would eventually get us there. Ultimately, though, when we do our substitution of variables, we end up with a rather complicated expression. Believe it or not, when it is fully simplified, it is a squared times the inverse sine of x over a plus x times the square root of a squared minus x squared all over 2. So, not really trivial, but it's workable. And then we actually do our substitutions. So when x equals a, we have a squared times the inverse sine of 1. And the inverse sine of 1 is pi over 2. So we have a squared times pi over 2. And again, when x is a, this one is a squared minus a squared, so that whole term is 0. Keep the whole thing over 2. The inverse sine of 0 is 0. And then when x is 0, this term is also 0. So even though it looks big and nasty, 3 out of 4 terms in that definite integral work out to 0. So this entire function, we have an 8b pi on the outside, and the interior becomes pi a squared over 4. So the volume of our torus is 2 pi squared b times a squared. So it seems like a lot of work, but this is the area of our torus. Once you learn polar coordinates, so instead of just working in x, y, z, you can work with things like r theta z, or in spherical coordinates, r theta phi. As you learn more coordinate representations, you will see ways to make this calculation easier. But you might notice that this simplified expression is equal to the cross-sectional area of our torus times the length of the circumference of the ring in the center of the torus. That is no coincidence. So that is another approach to eventually getting the volume of a torus, but this is the approach our current tool set supports.